In this portion of Chapter 12, we're going to look at some alkyne reactions. So alkynes, our triple bonds, are still considered nonpolar pi bonds. So we're going to see some similar reactions that we saw with our alkenes. There will be some slight differences though, because now we have two pi bonds instead of just one. So first off, we're going to see the addition of the strong acid to the alkyne. And here we're going to be adding that strong acid, something like HCl, something like HBr, to the alkyne, and it's going to end up generating for us the alkene. So with this, we have our alkyne, and I'm just going to show a terminal alkyne. So we once again have that difference in substitution of the carbon atoms. So to this, if we add our strong acid, we end up generating the alkene. And what you'll want to notice is that we are still following Markovnikov's rule in terms of that the halide, the second nucleophile, is going to add to the more substituted side. But the other thing that I want you to notice is that this is also an anti-addition. You'll notice that the hydrogen that we added and the X that we added, they're going to end up being on opposite sides of each other. So this is what we refer to as an anti-addition across that pi bond. If we look at this in terms of a mechanism, we're going to look at what I call a simplified mechanism. Simplified being that we're going to look at a very similar mechanism to what we have already used, where in actuality the true mechanism is going to be much more complicated because of one of the intermediates that we're going to draw on paper. But we are going to go through this simplified mechanism to hopefully help you understand and be able to predict some products based on things that we are most familiar with. So we have the alkyne. The alkyne is our nucleophile. It is going to attack our electrophile, which is the hydrogen of that strong acid. So initially when we generate this, we are going to generate the vinylic carbocation. And if you remember from some of our previous discussions, this vinylic carbocation is not very stable. It's basically as stable as a primary carbocation. So this intermediate truly doesn't exist for us. There's some other things that occur mechanistically along the route to get us to our final product. But again, we're kind of looking at a simplified mechanism, a mechanism that's going to allow us to convert from one species into the other under some of the rules that we have been looking at thus far. So we do notice that we are producing the vinylic carbocation, and the carbocation is going to be on the more substituted side. So from here, our nucleophile can come in and attack that carbocation that we have generated to produce for us our final alkene. One of the things that you will notice, it is going to go to the opposite side of where the hydrogen came in and added. Since we have that alkene, we have lost freedom of rotation, so we are going to see an anti-addition as we walk through this mechanism. One of the problems with this alkene addition with strong acids is it's very hard to stop with only one addition because we have generated the alkene. And the alkene is also nucleophilic under these strong acid conditions. So if we have excess of our acid, we go through the addition process multiple times. What we end up producing is what we call a geminal dihalide. So through our process, if we actually look at this under our excess conditions, we start off with our alkene, we start off with our alkyl halide, and we end up producing a species that has two halogens on the carbon atom. So this is our geminal dihalide, and both of those halides would end up on the same carbon atom because of our mechanism in producing the most stable carbocation. So this is what would happen under excess conditions. We initially produce the alkene, but that alkene will continue to react to get to the alkane. We can also look at the acid catalyzed hydration of the alkyne. So this is where we're going to add water to the alkyne in the presence of a strong acid. And this time we will end up forming a ketone. We form a ketone through the keto-enol tautomerization. So we will initially add the alcohol, but that alcohol is going to be on the double bond carbon, so it will be an enol. So that enol will undergo tautomerization to produce the more stable ketone. So the final product of this hydration is going to be the ketone for us. So if we look at the reaction, we're going to take that triple bond, put it in the presence of our water and our strong acid. Again, I'm using a strong acid that will not also behave as a nucleophile. And in this example with the terminal alkyne, we will end up producing the methyl ketone as well. So let's look at the mechanism for this reaction. So we have our alkyne, we have our acidic condition, so we have that H3O+. We're going to start off with that simple aspect of our mechanism once again, where the alkyne will attack the electrophilic acid, producing for us that vinylic carbocation and water. From here, the water, being our new nucleophile, will come in and attack that vinylic carbocation. From here, we do need to get our acid back, so I will take a second water molecule to deprotonate what we have just added, and that will get us into our enol. And our acid. But from here, what you have to recognize is with this enol, that enol under acidic conditions will tautomerize into the ketone, which is what we're going to show next. So it is that alkene, once again, that is going to attack the electrophilic portion of our acid to generate for us, once again, a carbocation. And that carbocation is adjacent to the oxygen of the alcohol. So through resonance, that generates for us a double bond between the oxygen and the carbon to move the positive formal charge onto the oxygen instead of the carbon. It is then that resonance form that reacts with the water that we created to deprotonate to get us back to our final ketone, as well as getting back our acid. So the second half of this mechanism is really that keto-enol tautomerism that we looked at previously, where the first half is this new addition across the pi bond. So because we start off with the alkyne, the triple bond, the initial thing that we produce is the enol, the alcohol attached to the double bond. So from there, it allows us to convert or go through the tautomerization under these acidic conditions to convert that enol into the final stable ketone.